That probably makes a difference. Testing, testing, testing. Testing, testing, testing.
You want to go move a couple slides just to
Yeah.
check.
You're good to go? All right,
Okay.
cool. Would you guys be able to send me the YouTube link later?
Yeah, we'll definitely send that.
Yeah. Okay, so let's go.
Okay, so we're going to do the intro today. Okay, awesome. Thank you so much.
You're welcome.
I'll be back. I'll tell you what.
Okay, sounds good.
Hey, good to see you. Good, good. Yeah.
So everything increased next 5 minutes. I think so most people are arriving in a couple of minutes.
Yeah, no
Sorry. Yeah, we're so many talks going on, lots of things happening. Back weekend, all kinds of stuff. So go on. Thanks for going. I'll distract you. Thank you so much for listening. You enjoyed it. I didn't want to hear it just to. Yeah. We've always. Thank you.
No worries. And then like 45 minutes or 50 minutes.
Usually 50 minutes, so but you can go a bit shorter or longer, it's okay.
Yeah, I'm tuned for 50 minutes. And from when we start or like ending at 4.
Ending up with 55.
4:55. Got it.
Yeah, so a couple days.
Yep.
Okay. Hi, everyone. Thanks for coming to the EI seminar today. Today, we're really excited to welcome Monroe Kennedy, who's currently assistant professor in McKee at Stanford and has traveled a very long way to come give us this talk. So really grateful for having him here. Monroe is a recipient of the NSF Faculty Early Career Award, and he directs the Assistive Robotics and Manipulation Laboratory, where the focus on developing collaborative autonomous robots capable of performing dexterous manipulation tasks. With human and robotic teammates. Monroe received his PhD in McKee from robotics in UPenn. Without any further ado, really excited to welcome Monroe.
Thank you very much for having me. It's a pleasure to be here. Today, I'm going to talk to you about our work in collaborative robotics and how it spans from dexterity to teammate prediction. So a kind of general overview of the work in our lab, we think about how robots can become better at completing complex tasks, how they can model themselves better, and then beyond autonomy, how can these systems perhaps work well with human partners? When I'm introducing someone to the space of robotics, I like to kind of give this huge kind of overview of the space, which includes the robotic hardware design. How do you make your system? The principles of robotic autonomy. How do you think about how your robot perceives this environment? How does it plan its objectives, and how does it actually make decisions and then control to the decisions that it wants to execute? And then beyond autonomy, how can these systems become effective collaborators? How can one robot conceptualize the behavior of other robots or possibly people in order to become an effective collaborator? And you can imagine many domains in which that can apply. So to kind of give a big overview of all the different types of work in our lab that span this space, this slide is meant to kind of capture that. Some of our work is in the space of dexterity, and I'll spend a lot of time talking about this one today, thinking about what is the hardest thing, the hardest challenge that we kind of identify that's keeping robots out of human spaces. And we identify that to really be dexterity. And critical to that point is really effectively utilizing the sense of touch and having that sense of touch approach the capabilities of what a human can do and possibly even exceed it. Some of our work also looks into how robots can actually observe a phenomena, and from that data, build an internal dynamics model to actually predict and possibly leverage and act on that prediction. We think about how robots can actually be better at completing sequential tasks, and how can you actually have effective queries from possibly human teachers, and how can augmented reality be a really nice framework in order to communicate that sort of abstract intent. We have work that kind of moves to the collaborative robotics side, where we say, can a robot watch people do a collaborative task, such as carrying a table, learn from watching them collaborate and become an effective collaborator? Can we take this notion of autonomy and the ability to predict what a teammate wants and even apply it to the space of wearable technology? So if someone has suffered a shoulder disarticulation and you want to give them this powered robotic arm, can you actually understand what they intend to do, given all of the decades of robotic autonomy, you may have a good idea of how to do a manipulation task, but really understanding which of possibly multiple tasks they want to execute could still potentially be a challenge. And we want to make that as seamless as possible and still provide them a sense of agency. And in the same space of wearables, can you imagine being able to predict where a person is going to walk in a cluttered scene? And if their stability might be challenged based on where they would walk, could you possibly alert them and, first of all, even understand that they may be at risk? And so this gives you a big overview of the kind of spaces that we cover. But today I'm just going to highlight these three projects and focus first on dexterity, and then these two projects in the space of collaborative robotics with some kind of high-level takeaways for how you might think about these types of problems. So to really motivate this, you can think of these two huge spaces that I think really motivate the need for robots that can touch and manipulate the world like humans. If you have the case of assisted living, it's really important that very soon we have systems that can augment healthcare so that people can better age in place. To be effective, it's one thing to be able to communicate with these people. It's another thing to actually be able to do physical tasks with or for them, such as even picking a pill off of a table and placing it in their hand. On the other side, you have this huge industry of manufacturing where it's still an unsolved problem to kind of do very small object manipulation, such as like assembling a phone. And there's a billion-dollar industry, multi-billion-dollar industry, where people literally have to do these types of tasks by hand, and not all of them are humane. So it would be great if robots could step into this field and potentially do these tasks that have been so far just strictly outside of the domain of robotics. And if you say, well, you can build these specialized sort of assembly line for these types of tasks, some of the technology changes so fast that that's not actually a feasible thing to do. So the field of robotics has grown immensely over the years. You have this one system on the side that's falling down the steps, and now we have Boston Dynamics doing backflips. Locomotion has been incredible. Perception has been incredible. Even sort of understanding your own proprioception, where your arms are, has been really well advanced with motors that we're able to use nowadays, but we still don't have these robots in our spaces. And if you have to narrow this down to one reason, I think it is robotic manipulation. And so kind of thinking about the importance of touch and where this domain might be really effective, you can think about some just toy examples here of detecting incipient slip. So when slip begins to happen, how do you detect it and react to it? If I want to assemble a very small object here, like this microchip board, how do I actually do that effectively? If I need to manipulate soft and deformable objects, how can I do that? Well, if I need to perform in-hand manipulation of an object, how can I conceptualize that and have a model that abstracts well for perhaps a learning mechanism to actually plan how it should manipulate an object in its hand? So let's build some fundamental knowledge here. So thinking about what's in a touch, we have this really nice taxonomy made by my colleague, Professor Mark Kukowski at Stanford quite a while ago, thinking about all the different types of grasps you might want to consider. And so if you kind of think of this broadly, you can have these sort of power grasps where the goal is to really immobilize an object. And then you have these sort of precision grasps where the goal is probably to do something effective with the object once you're holding it. And so based on what you're trying to do, this might definitely change the definition of what grasp success means for you. And to add to complexity of this problem, the question might also be, what type of finger do you have when you're touching this object? Is your finger really rigid, so there's probably a very small area of contact? Or could your finger potentially be very soft, in which there's actually a very large region of your sensor that's in contact with an object, even when that object is oddly shaped? So how does industry really kind of address this right now? Well, one idea is to kind of approach this from the notion of just build a very soft, deformable gripper. So here you see this really effective tool where you're able to use this soft gripper to actually grasp these objects in this space. And it does a really good job in terms of form closure. I can kind of grasp these, even fruits and things, without damaging them. But if I asked you, well, could you actually pick up a pill with this? That might be a lot challenging. And if I said pick up a pill and put it in a bottle, this might not be the gripper for you. So one way to accomplish this is to kind of move in your design space if you wanted to do something very precise, and perhaps think about something in the pneumatic range. So here you'll see this robot. It has these pills that are very smooth, that are placed down on this surface, and then it's able to take a picture, and then it used this sort of suction pneumatic gripper to actually adhesive itself to the different pills and perform this sorting task. So this works well on that kind of other domain, but there's a few key assertions that kind of have to be applied for this to work. One, your surface has to be very smooth, such that when you kind of try to apply this suction, you can actually hold it quite well. What if your object was perforated, right? What if it was larger? Is suction cup always going to work based on whatever material you have? What if the material was soft, right? So maybe it won't work for every scenario, but it might be still quite useful in some. And then the question is, well, do you want a more generalized solution? And what would a generalized solution look like? So again, building more fundamental knowledge and thinking about what we could potentially achieve, you have two areas to kind of pull from here: form closure and force closure. Form closure just says I've geometrically trapped this object. Force closure says I'm squeezing it, and between my physical contacts and the friction that's induced, I'm able to reject a certain amount of external forces or wrenches that might be operating on this object. And this is the sort of formal definition that has been used for the sort of immobilizing question in terms of grasp quality. But even if you can say, well, perhaps my system might not exceed the bounds of this and slip out, how good is my particular grasp? And so if I have a dynamic wrench that's being applied, I may need to know where I am inside of my limit surface, my wrench cone, in order to be effective. And that requires some sort of measurement. The holy grail would be a sensor that, if I could actually zoom in to any point on the surface, the continuum mechanics of this problem would be I could potentially at this surface get knowledge about my surface normal, my planar shears, as well as my torsion at every single point. So this is the best you could do in terms of forces for a surface. And of course, you'd probably want to know where the shape of that sensor is. Where is every point on that surface as well? If we kind of look at how humans achieve this, we have mechanoreceptors. These effectively sense vibrations, they sense pressure, and they're able to actually work together to send our brain signals about the types of contact that we're experiencing at our surface of our finger, with each mechanoreceptor being kind of responsible for about 3 to 4 millimeters, and they work together to kind of give you this high resolution feeling. And if you were to give someone anesthesia in their hand or in their feet, you can actually see that the quality of their ability to do many tasks greatly reduces. An interesting note is, this information is sent to this area of the brain, this particular cortex, and it's used to tell the brain this is the area that actually felt that contact when you touched. There was a study where they said, well, if we put a camera between the person and their finger and we show their finger being touched as we're actually touching them, and we actually show their hand being touched and we don't touch them, the area of the brain which is dedicated to giving you information for actual physical contact, if you have a very sensitive MRI, would still give you some feedback saying, hey, something should have happened here, which is amazing that we have this ability to actually be able to actually correlate vision, right, to the sense of touch, even though physically there's no connection there. And so maybe one day there'll be a very cool octopus that has eyes in its hand, because that might actually be very effective as we're moving towards. So the types of tactile sensors that exist, there's the physical transduction, optical based sensors. For the physical transduction sensors, they're very good. You can get good readings for them, but it's really hard to get multiple modalities of sensing at a very localized high resolution area. So if I have a capacitive sensor, I could have an array of capacitance, and that could be good for sensing surface normal. But if I said I also wanted to get the shear and the torsion, you might have to make something more complicated. And this is a recent paper, again, out of Stanford with Mark Kukulski's lab, where they're actually detecting the deformation or the motion of these nibs, and they're using the differential in capacitance to tell you what type of force it's undergoing, normal, shear, and you need a group to actually give you some notion of torsion. But as you can see, things are kind of really spaced out for this. How do we think about perhaps getting more information at a denser area? So this gives you the whole space of optical tactile sensors. And so here, all of them are really looking at how can we have a camera that looks through and is able to see the contact area. And here you can actually see in this gel slim paper, you have these dots, and they're actually tracking that deformation. You can tell a little bit about the types of force, the shear that's undergoing as it's performing this manipulation task. And they're shrinking down. Some of them are flat and small, others are kind of small and more circular. But usually they're also pretty rigid. They're soft because they actually have to track the strain. But if you try to really deform them, they don't deform an extreme amount. So, this paper did a really nice job of outlining what would be the holy grail for robotic touch. And I happen to agree with their summary. It would be great to have something that's high resolution, highly sensitive, reliable, easy to use, compact, and inexpensive. So this led us to design DenseTact. And so our first generation was quite large, but operated under this principle that we could actually observe the deformation of the surface and then have a very unique calibration method that would allow us to actually perform regression so that we could tell you the exact metric distance of every point on that surface of the sensor. And so again, we're not alone in this space at all. There are a lot of different applications here that kind of try to use the same thing, and all of them have these similar components. You have this sort of soft gel, and the softness varies based on which one. You have some interior LED illumination. You have a camera that's observing the interior, and you have a sensor housing and possibly some off-site computation. For this first work, we really wanted to drive home the resolution for the shape sensing, and that's what I'll kind of get into now. So for this first design, these are the design qualities, but at a high level, we have this elastomer, a very, very soft silicone gel. We have this sort of silver paint that we put on the boundary of the sensor. We have these LEDs that illuminate the interior of the sensor, a 3D printed housing, and a camera that looks through to see the interior of the sensor. So I'm going to talk briefly about the camera calibration, how we did that for shape reconstruction, talk about how we modeled it and calibrated it. So for the camera calibration, when we first started off in 2019, we didn't know anything. We were like, let's try putting a bunch of cameras inside of our finger. That was very computationally expensive and very large. And then we said, well, if we want to see the interior of this sort of dome-like hemispherical finger, what if we actually try to use a fisheye lens? And it turns out that that was a very nice move because if you actually align the center of your fisheye lens with the center of your hemisphere, you get this really nice property of equal angular projection. And so essentially all that means is the distance along the exterior boundary, the angle that you pass through, correlates very nicely in the ideal lens case to evenly spacing on the lens that's being, the light is being projected onto. But in reality, this is never actually perfect. And so you don't actually get this really nice linear relationship between the sort of latitude angle on the surface and the radius from the center of your sensor. Instead, you get this slight curve, which you could approximate by some polynomial, or in our case, we used a Gaussian process to perform that estimation. To calibrate that, we did the following process. We kind of 3D printed a part that we pressed in. We knew where these were from our CAD model. We were able to measure the pixel distances here, and we were able to numerically fit that curve. And we decided to do that with a Gaussian process and perform the inversion. So given any point on the surface, you could tell where it should actually be reprojecting back to the surface of our sensor. So to first understand this sort of shape reconstruction, we can talk briefly about how this kind of principle works. So if I have a surface and it's kind of perpendicular to the camera, the LED strikes it, it's extremely bright. If I rotate it, it's actually going to get dimmer. And you can actually relate the surface normal that you're sensing to the angle, to the intensity of the light for the sensor. Given all of these surface normals, the name of the game begins to be, how can I actually reconstruct the surface given that I know all of these normals? Well, if you know some boundary conditions, you can actually perform Poisson integration to accomplish that. But in general, this is really challenging to do because if there's any disparity between the angles that you're kind of measuring from light intensity and what it actually is, performing that integration can actually be imprecise and you won't get a very nice connection in your surface. So what the literature has traditionally done to kind of get past that is to use a sort of lookup table, and then you can decide what resolution of lookup table you need in order to actually kind of perform that sort of numerical integration. Alternatively, you might say, well, this is the problem I'm trying to solve. Could we potentially use a neural network to perform that Poisson integration for us? So that was our approach. So we said, well, can we actually print out these 3D shapes using a 3D printer? We know the shapes because we CAD'd them. Now we're at the mercy of the resolution of our printer, an S5 Ultimaker, so about 100 microns. Can we actually push a combination of these patterns into our sensor, perform ray tracing to construct the expected depth image after pushing into that sensor? Using this, we can now do supervised training. So I have this, this input image, I'm feeding it through my network, DenseNet, CNNs with skip connections, and the output image needs to be the depth image for touch. So where is every point on that sensor? And this is the interior view. I can then say, well, I know the expected answer. I know the part that I'm pushing in and its configuration. I can perform a loss here and train my network to get the output dense image. And then I can easily go from that immediately to a point cloud. And so this is the sort of performance with our training set. And you can see here that for a holdout set of 1,000 images, we're actually able to do really well on the order of about 200-ish microns for the error for this holdout set for our system. This is a violin plot, so it shows you the distribution of our data over those 1,000 images, and then it's the megapixel image. So some really cool applications, we could perform some really brief in-hand localization using ICP. I'm going to jump to this particular part in this video, if it plays, hopefully, that really shows how well we can do when we're touching an unknown object. So here I'm pushing a screw that was not in the training set into the image. You can see the deformation here. You have the depth map from our regression integration, Poisson integration from our network, and then you can see the point cloud that's reconstructed. One thing you'll notice is you can actually see the threads in the raw image, but they don't show up here because the size of these threads was actually higher than the resolution of the printer. So it wasn't that our model couldn't potentially learn it, it's just that it wasn't in the supervised set when you were performing the regression. So that was great, but then we wanted to kind of add forces to the mix. So we created DenseTech 2.0. So to that end, we said, well, if we want to add forces, like others, you need to actually have markers. A very popular approach is to actually just put dots on the surface of your sensor and track those dots. If those dots for the softness of the sensor are too close to each other and you perform deformation, you can have this sort of aliasing effect under pure shear. And so one way to get over that is to then track the deformation over time and say, okay, I actually observed this motion. I need to keep track of it. That can be computationally expensive. Alternatively, you can imagine giving your sensor a very complex pattern inside, such that when you deform that sensor dramatically, you're able to say, actually, I know what the original shape was. I can actually avoid that aliasing effect if my sensor is extremely soft. So our first attempt was to use a hydrographic film. It's like this sort of papery material, floats on the water. You dip your sensor into it and you get this display. And that's what you see here. The challenge was that because it's sort of like an oil pattern, the pattern density was not uniform over the sensor. So this first one you can see kind of like hooked up on our Franca arm with like a camera on top and holding an object and what that might look like. So this brought us to the final version of our sort of pattern deposition. And so what we essentially did here was we used Voronoi tessellation. So we had points that were evenly spaced all over the surface. And then we used a traveling salesman method to actually connect all the dots without crossing any lines. We put this on a stamp, which we then stamped by hand. Because we stamped it by hand, no two sensors are alike. And the colors that you see here is just taking that raw image, putting it through a dense optical flow. Colors correspond to direction, magnitude, the intensity of that deformation. So this is the exploded view of DenseTech 2.0, camera, LEDs, very soft gel, the pattern that we deposited, and then our silver silicone spray so that the whole thing is homogeneous in terms of being silicone. And then this is being applied holding an ATI sensor. We get a 6-axis wrench. We're just reporting for ease here, one axis and showing that it corresponds well with the axis that you're measuring from this ATI sensor. You have the depth image, which creates this point cloud. And then this is the output force within a few newtons of the ATI reading. So kind of thinking about how this fits into the big picture, it's very similar to what we said before, but now we're really focusing on what we can do in terms of that sort of force deposition and tracking using markers to track those force estimations. Comparing DenseTech 2.0 and 1.0, we have a fraction of the volume, so about a third of the volume. We are at an even cheaper sensor cost. So the camera we're using still costs about $70. But everything else brings us roughly up to about less than $85 to $90 with this, or well under $100 per sensor. Again, kind of looking at that exploded view, it's modularized, so it's easy to take apart, put it together. Again, you have the LEDs that you can control the brightness. You have this housing that is able to have this reflective interior to help shine the light into the center of the sensor. We have the pattern deposition technique that I mentioned. We have the camera module, LED module, gel module that all fit together for your sensor. To collect the position, we take this sensor and we attach it to a CNC machine, and we actually run this through all of these different touch points in order to collect the data. And you can see that in some cases, you're well over 30,000 touches in order to train even one sensor to do a decent job in regression for the shape estimation. To train the forces, this is how we did it. We had different kind of tips that we then touch our sensor with from different directions. And we actually are able to map the image that we see, the deformation of these points to a 6-axis wrench measured from this ATI sensor. You can then transpose that wrench, the torque component, wherever you like with simple mechanics. To do this, we again used a neural network to perform the Poisson integration, and we also used that same sort of architecture to learn the forces as well. We kind of benchmarked two methods: a Swin transformer that looks at areas of your image and then understands how those kind of build together to give you your output. We compared that with DenseNet, which uses convolutional neural networks in this autoencoder structure as well. And what you can see is that we were actually able to achieve comparable performance in shape for sensor 2, similar to 1. And we have this ability now to also measure the forces and torques as well. Some key takeaways: we were able to achieve 0.36 millimeters L1 error per pixel for shape reconstruction on 1,000 images, and 0.41 newtons for forces, 0.38 millimeters for torques. And we also said, well, you know, that 30,000 touches is not trivial, even if my student can kind of leave it on the CNC machine and go. So with transfer learning, after you train the first one with comparable sort of material properties, we show that you can actually achieve the same similar performance with 12% of the data set size if you use transfer learning. And that means allowing all of the weights inside of your model that I showed before to change. These, again, are the sort of violin plots for the data. I'll draw your attention to the test set data, and particularly for DenseNet, which performed better. 2 modes. This is likely due to the area of the sensor that didn't have anything interesting on it. So pay attention to this one. This bounds our performance for an L1 error in terms of milliliters per pixel on the 1,000 images that we looked at. These are similar results that you can see for the forces that we're able to measure. Again, DenseNet on this bottom row performed quite well. This plot shows the forces Fx, Fy, and Fz, the torques as well. And you can see that comparable performance for the test and the train. So pay particular attention to the dark green for the test performance. Again, kind of talking about that transfer learning validation, we were able to do this for both the wrench as well as the shape reconstruction with only a fraction of the data, so less than 5,000 points in order to do the same thing. So we're training in a fraction of the time for our sensor. So what can we do with this? So one of our ongoing projects that I'm very excited about is manipulating objects between the fingers. So if you actually have these kind of dense tack fingers, just thinking about shape, not forces for the moment, can I reach into a bin of screws, grab multiple screws, and then once I do some classification to know which screws are there, could I potentially roll my fingers on each other to select a particular screw to perform sort of like bin sorting? So to kind of achieve that, we kind of built our own little Dynamixel gripper. We attached our hands. We can reach into this bowl, grab screws and nuts, and then perform this sort of sorting task. And this is ongoing work, which we hope to have completed shortly with screws that are even smaller than what you see here, to kind of really give us a chance to work on that control in terms of rolling the fingers together for very small part manipulation. To achieve this, there's 2 ways to kind of go about it. One is, really leaning into the domain that you know you're in. So if I know I'm picking up a screw, I can actually perform some basic computer vision techniques to extract important features like the length dimension of the screw and the head of the screw. If these become a feature space, I could then perform classification to determine which screw I'm holding. But more generally, I might want to think about saying, well, if I kind of know the region that I'm looking at and I can be sort of pose invariant, could I classify that directly? And this is a target architecture. We're trying to achieve that. This is important because we believe that we may actually be able to extend to other items really quickly, specifically the contact and sorting of pills. And so here you see this sort of Tylenol pill 438 is written on the surface. You can see the rough circular geometry. You push in. If you watch this video again on YouTube at very high resolution, you can actually see the 438 there, and you have this sort of density map. This is an artifact because this is just a quick sensor we were doing a quick test with, but usually you don't see that sort of artifact. And so you can imagine being able to figure out the geometry of the sensor, and then once you know the region of the camera of the touch that you're interested in, you could zoom in and search really easily to find the writing, and then that's a really cool way to actually make sure you're about to hand someone the right pill. Another really cool application is the use of touch to augment neural fields, so our nerves. So if you're unfamiliar with nerves, they're a really cool tool. More than 90% of the images that you're seeing here are synthetic because they're interpolated between real ones. To actually achieve this, you're having a neural network that's shooting a ray through space. Along that ray, it's answering what's the density and what's the color along that ray. And then it's able to tell you from multiple perspectives what the volume actually looks like. And so what's really nice is, well, you know, the challenge is if you kind of think about touching clear objects, this can still be quite a challenge if you wanted to say, okay, this will look right with a regular nerve, but it won't have the right volume representation because any light-based method won't do quite well with transparent or reflective objects. But if I can touch that object, right, then I can actually use touch to augment that neural field. And so here you can kind of see if I have this sort of depth image inside of my finger, I can touch this object, gives me a depth image. And then that can actually augment my nerve and allow me to actually do a better job of constructing this object with a neural field, and perhaps even using that combined representation to get other object properties and have a brand new way to represent or provide a digital twin for objects that I might want to manipulate and hallucinate future observations, be it camera or touch, if you've done it enough to collect it over this object. Kind of leaning into like how we might use this for force-based tasks. A question we're asking is, well, what if we're touching a very soft object and perhaps there are beads embedded underneath and I want to feel it kind of maybe moving toward use for tumor detection on a person? How could I potentially achieve that? So to kind of set this up, this is work that's ongoing, almost complete. And what we're doing here is you have this sort of dense tack sensor that's pushing into your surface. You have this foam that's on top. You have beads that have been arranged in a way that you can actually collect an image to know where they are for ground truth. We've kind of clustered them together so that we can actually perform both a sort of exploration and mapping to efficiently build and reconstruct this underlying lumps under this soft surface toward that sort of medical application. And so this kind of shows the whole paradigm. You collect your samples, you have measurements for both the wrench and the shape. That feeds into a probability distribution about what you think is the presence of beads under the surface. That feeds into a Gaussian process that's been trained for this particular type of clustering of objects, which tells you what your next best touch should be to build a map as quickly as possible with the fewest number of touches. DenseTAC 3.0 is on its way. So we went from one that is a few centimeters tall now to one that is about 1.2 centimeters on edge, about the size of a human thumb, the average thumb. The kind of explosion is very similar. What's different, we've kind of fabbed our own boards here for the LED. We have Arducam that kind of fits in here. We then fab our own lenses, and then everything fits in as shelves. And then you kind of fit your gel in on top. So this first one was kind of flat. We were going for skin by having an array of these. They're only $30 per cell. But now we're kind of going back to a more curved shape because we realized shooting for the stars, we landed on the moon for a much smaller finger for our system. And so, yeah, this is the order. If you're interested, I brought one of these boards with me. You can kind of see it for scale after the talk. So kind of thinking about what does it take to actually perform good shape reconstruction. I kind of mentioned that we kind of 3D printed these objects, but I really didn't give a good insight into how we actually came up with that. And so there are a few principles that we employ and we could employ, and what we're going to do for our next sensor, which is thinking about how for that surface, we need every point to be in contact. We want it to be sharp and have interesting features, but it shouldn't be so sharp that it would cause the gel when it's touching this object to kind of diverge and break off of the surface. And then we need to make sure that we actually have at least one point when we're fully in contact that's not deformed to make sure that we kind of ground ourselves and don't have a distribution shift. And then make sure that we have interesting features. And then this can become a very interesting optimization problem in terms of saying, if I have control points that I'm interpolating, how can I control their motion in order to create these objects? And so if I have multiple surfaces that I'm touching in, I'm maximizing the entropy between them while maintaining these stated constraints. And so with these, you can do some very interesting things, hopefully in the future in terms of finger gating to even with this type of model, if you have depth images, if you have a high resolution force information, force field, can you actually talk about finger gating and even reveal this to a learning model to train? So at this point, I'm going to kind of shift gears. So we've talked about dexterity. We've talked about how you can actually have these systems that might be able to manipulate human spaces. But let's jump to the other end of the spectrum, right? How do we actually have effective systems that can perform teammate prediction? So to that end, we can look here and see one first thought is thinking like, how do robots think about what other teammates might do? And this leads us to this whole notion of theory of mind. How do I think about what you're thinking about? And am I thinking about that you're thinking about possibly me as well? That's theory of mind, first and second order. If I give you this toy example, right, these two agents trying to carry a table around an obstacle to some goal location, I can kind of phrase this in a sort of control framework. I have a robot policy, a teammate policy, there's some world dynamics. Both agents are able to observe what's going on, and this loop closes as they're trying to perform their objective. In a centralized system, arguably the best you could have, there's clearly one objective, which your centralized oracle has decided on, and it's controlling what every agent in that system can do. The interesting case which we're looking at is the decentralized system. And so then we have to first say, where A, do you have the same goal? And B, if you're trying to do the same thing, if there's agreement there, are you capable of actually executing that task effectively as a team? So thinking about the modes of control, on the one hand, you have reactive control. So you simply know where the target is. You don't do any sort of planning. You're just trying to respond to your current state. The other is where you might actually take into account how both your objectives and possibly other factors in your environments, like this local minimum presented here as like a barrier or a hallway, might influence the way in which you decide to move. And if you can kind of take this sort of planning mechanism into account, then this may need to be a part of your teammate cognition model in order to understand how they would plan around these more complex barriers as you're trying to execute this as a team. So the very first question we have to ask for is first, do you agree on your goal? If you do, then you can directly use that to inform the policy you think that the other agent would do and hopefully predict their expected behavior. If you don't, then the very first thing you need to do first is reach consensus in order to be an effective team. If you're trying to reach consensus, you might realize that there might be different frameworks you might be under. Is there a hierarchy? Is there a leader follower? Or perhaps is there some sort of voting that needs to happen between equal partners? And then another question you might have is, where does that sort of source domain knowledge come from? Did it get demonstrated to the robot? Did the robot have the chance to interact in the environment before before it began to do some sort of collaboration? Where does that prior come from? Is there a prior that you're able to leverage? And then after all of that, depending on how many agents you're collaborating with, another consideration is, how do you effectively perform these rollouts in a computationally tractable way? So I'm going to kind of present two projects that we're doing that kind of looked at aspects of the factors that I mentioned here. The first is human-robot cooperative transport. So under this sort of paradigm, as I kind of mentioned in the beginning of the talk, we want a robot that can learn from humans performing a task, be able to extrapolate different options, and then execute what it thinks will be the best option as a collaborative team. This is the architecture that we use to execute this. So we observe, again, how humans work together. We observe how our collaboration is going. This creates for us a latent strategy, Z of T. We can then have motion predictions. We select a plan and then use that to execute a rollout To compare this, we kind of looked at what you might choose naively off the shelf. One might be the sort of RRT method. So here I'm planning just feasible trajectories and then controlling with a PID controller along those trajectories. And there's a human on the other side that's trying to work with me. Because I'm not taking that human's actions into account, you can see that only a fraction of these sort of rollouts perform quite well. Whereas if you do this variational recurrent neural network approach, you're actually able to do a much smoother long-term prediction. And in fact, you can see this collaboration works quite well empirically. Another kind of way to get deeper insight into that collaboration is to actually look at the interaction forces while the agent is executing this. So the interaction forces just say, there's a wrench force that's moving me to my goal or causing motion of the table, but there might be also some forces that when they sum up, they are equal and opposite. And so they don't result in motion of the table. So they would either compress or stretch the object. And depending on how large they are, that's probably a really bad use of your energy. And so you might have some interaction forces to carry an object, but they probably would be bounded if you were collaborating well. And so decrease in that interaction forces below a particular value is usually associated with teammates actually reaching a form of consensus. And that's what you see here for comparing these two modes, VRNN versus decentralized RRT. We also did a study where we actually looked at how humans might do in terms of predicting whether or not they played against a human collaborator or not. And we had a very fun result that they actually were kind of confused under the VRNN case. So again, violin plots to show you distributions over the number of players that are there. Each color represents each method. VRNN is the proposed method, that's in orange. The kind of indexing here tells you who the human guessed and what it actually was. And you can see that we actually did quite well in terms of the human predicting that it was a human when in reality it was a robot, created decent confusion. Another sort of area to kind of look at this type of sort of cognition is in this sort of more passive fall prevention wearable sensor. So the question we asked in this project was, can a person's balance be affected by external factors? Can that be predicted from environment observation? So if you think of everything that might cause a fall, you could think of internal causes like illness or psychological factors, as well as external factors like maybe someone actively perturbated the individual, or maybe there was more passive perturbation. So our goal was to say, if I put a wearable sensor on a person, let's say a camera IMU on the torso and IMUs on the legs, can I actually use that to collect information about the surroundings? And then along with these other features like the person's step frequency and motion and tracking their torso motion, can I predict A, where they're going to go in the environment, and B, how stable or how balanced they may be? But the challenge is balance and stability are very contentious terms in this sort of field because it's really hard to predict and have an agreed upon metric. So to kind of start off, this is our sort of data collection method. This is the camera mounted in IMUs on the legs and torso. Our sort of problem statement, right? We have this state, which is influenced by the person's intent and surrounding environment. We'll represent that with this form Z of T, and we wanted to predict what those future states were, what the human intended, and how their relative perspective to the environment would evolve. So the state included the pose of the person, the torso velocity, this thing we called sway covariance, and I'll get into that in a second, the step frequency and joint angles. And then our goal was to predict the future sequence of states conditioned on the environment and past states, and also predict how our environment would evolve conditioned on the past environment and past states. So the first challenge is, right, if we want to use this sort of data-driven approach. How do we actually represent this in an efficient, tractable way? So what we used this sort of depth panorama. So if you literally think about a panorama as a sort of cylinder surrounding a person, you can actually get a point cloud to start, project that point cloud through to the panorama, and create this sort of panorama depth image. So the center of the image is in front of the person, and then the edges of the image are behind them. So this red line cuts and unfurls to this sort of rectangular view. The person's steps are in front of them. The tree is off to their left, and you can kind of see that in this sort of cartoon image. And so the very first step is to perform image reconstruction. Take this panorama image, use an autoencoder to compress it to a latent space, and then reconstruct it. The sway covariance was a little bit more challenging, and this is where our partnership with Professor Steve Collins' group really came into play. So they have these people walking on this treadmill, and they perturbate them at specific times, and they can watch their full torso motion. So to kind of think of these two kind of pull weights at 7.5% and 15% of their body weight, if you actually just track the orientation of their torso, you can see a sharp change in that sort of theta or deviance from the upward direction, or world Z, at the time 10 seconds when they were perturbating, and it was visible. But if you actually track these values, it wasn't a really big jump. Alternatively, we said, well, what if we actually track the person's torso motion over time and created this sort of covariance area? How well would that perform? And so here you can actually see, by tracking that covariance area over time, we get a very sharp signal in this sort of active perturbation. So we combined all of that into this following architecture. We said, if we watch how the person is walking in time, we can create these depth panorama images from all the point clouds that we see. We project them into this panorama image. We can use the autoencoder that we train in training time, and then we can remove this reconstruction when we're ready to actually execute, but this is the loss for that. We have this sort of latent representation of the obstacles. We also have the odometry, joint angles that we can compound into this state. We can then use this combination of LSTM MLP to perform this sort of temporal rollout of where we think the person will walk and how will the environment change around them as they walk in that particular path, and perform that construction of that future path. And then these are the losses that we have for the state and the panorama output for that long-term prediction. So these are the different paths that we walked around on campus. This is the performance of our system for position, covariance, ellipse area, and the velocity meters per second in indoor, outdoor, cluttered, and outdoor free environments. The shaded regions is the first standard deviation. Zooming in specifically and thinking about the role that vision and observing the surroundings gave us, we saw that particularly in the outdoor cluttered environments, that we were able to see an extreme benefit from obviously looking at the surrounding environments that included that knowledge in prediction where you were going to go. So this is showing the kind of rollout for the system in time. Blue area is the covariance ellipse above the person as they walk. Orange is where they're expected to walk. And then you have this sort of orange line and green line. Orange is where they actually went, green is what you're predicting. And you can kind of see this in this sort of time sequence, A, B, C, D, E, F. What was nice too is we were actually able to do a decent job of predicting the growth in that covariance ellipse as a function of the environment that they were walking around, which meant that now with this kind of tool, if I'm predicting that there's going to be a sharp kind of spike based on how you're walking in the surroundings, now I can do something about it. I can alert you, or I can possibly alert a lower limb exoskeleton to perhaps improve your experience walking in that environment. All right, so I want to quickly just show the end of this video, particularly like how it looks when this person walks in the environment. So this is an RViz walking in this room, this sort of first person, and then this is the top-down view. So he walked to a dead end. The model predicted that he would kind of turn down the hall, but he actually was going to turn and do a U-turn. And so the model adjusts and then begins to predict as he walks. It's not great about windows. And as he'll kind of like demonstrate, there's this window that's going to pop up on the left. It's going to predict going through those glass doors. And there you go. and then predicts, making this sort of right-hand turn and is able to kind of predict. So this is where we're currently at. This is in ICRA 2023, showing our ability to predict that kind of covariance in future path. So what's next? One, it will be great to be able to predict multiple paths, so have a multi-path hypothesis. So where of all the places you could walk in a scene, where are you expected to walk? How can we actually put this model onto a mobile device so that if we want people like the elderly to be able to leverage this type of tool, that it can actually be relatively easy form factor for them to actually utilize. And then we need to move from our younger adult population to the communities that might benefit the most from this, like older persons, and perhaps those with different disorders that could really benefit from this tool, and even think about how we might apply this to lower limb exoskeletons as well. I'd like to end here acknowledging all my amazing PhD students, all the amazing master students, and grateful for all the sponsors that we've had to date. Thank you. Yeah.
In the example you have with the film and the indentation, are your sensors now able to identify material as well? So could you discern between? Hello? Can you discern between like the real pill, or if I had machined or 3D printed a pill, could you discern which one it is?
That's a fantastic question. Just for anyone who missed the first part, it was like in the case of like detecting pills, can you actually discern different materials? And perhaps if there was like a metallic pill versus maybe a ceramic or actual pill, could you actually determine which one? That's a great question, right? So I think there are certainly certain cases where it's really easy for me to say, yeah, probably you could, right? So I'm gonna back away from the pill example you gave me and say, well, let's say I was trying to detect something of variable softness, but maybe similar geometry or differing geometry. Those, it's probably even immediately kind of obvious to you that you may be able to detect between a real and fake one. But the example you gave is actually really interesting because the kind of question that kind of poses there is, what is the state difference between, for instance, a regular pill and the metallic pill? Well, we both know that one you can crush and the other you probably can't. If I wanted to kind of really squeeze, I could crack a regular pill, and maybe if it was metallic, I couldn't. But if I didn't exert that much force, then the question is, what are the other properties that I could be extracting from that sort of situation? Maybe the temperature, or maybe there's sort of a pattern that you might see on that surface that you could potentially extract. So if that information was available to you, such as the pattern, for your pill might, if it's kind of like this sort of, again, ceramic-y kind of thing, maybe it has its own kind of pattern that the metallic one doesn't. That could be a differentiator in the state space that you might be able to recognize. But if that's not present, then that's a challenge that you have, and you might consider a sensor that would reveal the differentiating state that you care about. So there are some sensors that use, for instance, temperature to try and determine between material types.
And is that something that you're looking to implement, or is that something that you're not looking to implement in your specific sensor?
So for now, we're trying to do the best we can with a single camera. And that camera is like a regular RGB camera. You could imagine if the kind of task that we were trying to do was motivated to, we could imagine putting in, for instance, a thermal camera to kind of accommodate that. But for now, we're trying to get away with as few sensors inside that we can. So RGB is the primary focus.
I just got an idea. Maybe you can just put like a temperature sensitive, like a paint, and like you can just turn off the LED and you can just read it out directly using the same sensor. Yeah.
That's actually a really great idea. I actually recently saw a paper that was doing something very similar to that. So you're right on target. The challenge with that is, again, the sort of LEDs that we had were kind of color based. So you'd have to be very clever in the kind of domain that you select so that you don't get mixed signals between color changing due to temperature and intensity light changing due to the surface normals that you're trying to predict.
Do you have the ability to actually like turn the LED off?
So you could, right. So then, or even change the color. So exactly. So you could imagine a version of that you could do that. But then when the light is on, you may want to make sure you don't have a mixed signal, but you could potentially do something like that in a design. Yeah.
I had a question also about the sway covariance.
Yeah.
So it seems like after the perturbation, there's a big jump in covariance.
Yeah.
Is there any predictive power for like prior to a fall that you see some sway covariance as well?
Absolutely. So if you of the types of falls that you might experience, if someone were to like from an upright position, collapse directly down without their torso really changing, this variable would not be helpful for you. But if you would pitch at all before that happens, then this variable might be useful for that kind of prediction. And then the thing is, for most people, falling isn't very simple. Like unless something extreme happened, you don't just have like a constant velocity and you're just pitching, right? Usually there's something that's going to happen before that occurs. And that's where a lot of the kind of complexity to date has really come from, right? If I'm walking up a set of steps, even if you've kind of ever slipped in like a grocery store or a wet floor, there's usually this, or ice, because you guys live in a place with ice. Whenever you start to slip, there's this whole dance you do. Try not to go down, right? And that dance, right, is really, a change in your natural sort of gait, that your torso would experience, right? And so that ice is an extreme example, but even if you were to like stub your toe when you walk up the steps, you pitch quickly forward to kind of catch yourself. That's a deviation from your normal motion.
Yeah.
And so if I can kind of correlate that to the motion that I've seen you walking at, so maybe you're walking way too fast for these steps. And for your kind of group that I've trained this on, maybe an older person or someone with a disorder, and maybe even younger people, if I go, usually walking at this pace, given the steps there, you're not walking in a way that statistically means you've acknowledged that risk. Therefore, there is a likelihood that you might pitch, right, extremely when you reach that interesting feature.
And that's one of the challenges. So our lab, it's not my project, but other people in the lab have been trying to predict falls. And it's challenging because if you want like a long time horizon, then you have to have a high, or you usually end up having a high false positive rate.
Yeah.
Which is not good. So that's a very interesting metric.
Thank you.
Exactly. Thank you. I was really interested in the dense tact work and specifically the future work section and the power of detecting things like incipient slip. I was curious if you're close to cracking that problem and if there are any gaps between what you currently are capable of and what you need to achieve.
Yeah, so I'll start off by saying we're not the only ones at all who are doing the incipient slip. There's a lot of work in that space, even with gel slim, kind of to look at that. And usually what you'd expect to see is, there's this kind of force that's exerted, and then maybe there's a part of your sensor that's kind of like snapping back to its original thing and it's non-uniform, or maybe the object should be in your hand, but it's actually like, relaxing instead of maintaining that particular stress. So, that's a very important problem. And we're not the first to address that. The kind of power I would say we can bring to that conversation is, well, what would it mean and what value would it be if I were to say, not only is, slip occurring and here's where you are in your wrench cone, but here's actually a metric value for the stress field that your finger is exerting, right? And then what would it mean to kind of plan a multi-contact, right? Or change the positioning of your fingers in order to perhaps minimize that likelihood. So think about grasping a slightly wet wine glass, right? We can kind of press and hold and we can feel some differences, and we can say, well, we can reason about if I move my sort of hands down, the stress distribution will actually shift as I kind of move my fingers along the side, and that will result in a sort of stable pose. Now, we know this from experience. You want to frame this mathematically, it's a slightly different kind of conversation. And so kind of thinking to that end, there may be certain scenarios where having knowledge of the stress field might greatly inform your ability to predict the quality of your manipulation, and that form of representation might be very useful for a model to actually do its own cognition and plan sequential grasps to do interesting things.
I agree. Thank you very much.
Sorry, yeah, I think this room is reserved by afterwards. Maybe for any other additional questions we have, maybe people can come up and just directly ask in person. Again, really thank Monroe for giving a great talk today, and we're super excited that you got a chance to visit us.
Our pleasure. Thank you.